Lesson 2.5 is complex zeros and fundamental theorem of algebra. We are starting this lesson today, but we're not going to get all the way, well, we were never going to get all the way through it to begin with. We're really not going to get all the way through it now. Okay, so make sure you're in the notes with me. Put the iPads aside so I know you guys are in the notes with me and following along here. Okay? Fundamental theorem of algebra. Some of this is going to sound familiar, okay, because we are building on what we've done in the past. But notice it says complex zeros today. So when we talk about complex zeros, complex numbers means we are including imaginary numbers. Okay, so when we talk about complex numbers, that's imaginary numbers. So looking at that IXL problem is a good lead in here. Fundamental theorem of algebra. A polynomial function of degree n has n complex zeros. So previously we talked about if a function is degree n, it has at most n zeros, right? That's when we're talking about real zeros. If it's degree 3, it's at most 3 zeros, but are actually at most 3 real zeros. There's always 3 zeros is what I'm saying now. However, they're not always necessarily all real. And so we start talking in the complex, okay, so a polynomial function of degree n has n complex zeros. That means altogether, if it's degree 5, there are 5 zeros. Some of them might be real, some of them might be imaginary, but there's 5 zeros. Okay, so complex, if you recall, is that a plus bi form, and that can represent real, that can represent imaginary. Okay, and there is also the possibility that some of these zeros may have a multiplicity greater than 1. Remember, multiplicity is the power on the zero, and if something has a power of 2, well, that counts as 2 zeros. Okay, so we'll talk about this as we go. We're also going to talk about the linear factorization theorem. Given the function f of x of degree n, assuming degree is greater than 0, then f of x has precisely n linear factors, given in the form there where a is the leading coefficient. So again, degree n linear factors. But keep in mind that makes sense because each factor represents one of our zeros. So degree n zeros, n linear factors. Now this next one is hugely important. Complex conjugate zeros theorem. Okay, so put this in your brain, hold on to it because we'll use it here in a little bit. Given function f of x with real coefficients, so not just real coefficients in there. If a plus bi is a 0, then so is its conjugate a minus bi. Okay, they're real good about, they'll give you one imaginary root, but they won't necessarily give you the other. And so you have to be able to identify, okay, if they give you a root that is a complex root that has a imaginary part, a plus bi, then you also have to include the conjugate. And that is this complex conjugate zeros theorem. Okay, so keep that in mind. Watch for that. We will use that as we go through this. Now, real quick, before we move on, because we're going to talk about I today, what is the definition of I? I is equivalent to what numerical value?
Square root of -1.
Okay, I is equivalent to the square root of -1. We know that, right? We just have to dig deep to remember it. The other thing I want to review, I squared is the other typical one we'll use. So if I is the square root of -1, what is I squared? Not 1, -1. Because what happens when you square a square root? If we square the square root of -1, what happens when you square a square root? You get whatever's under the square root. Okay, so this is review from Algebra 2, right? Review from about a year ago. I think I introduced this later on in Chapter 4 in what I'm doing right now in Algebra 2. Okay, but remember this information. We're going to use it. Okay? Okay, example 1. They're giving us a polynomial here, and I think there's about 3 things they ask us to do. They're going to ask us to write the polynomial in standard form. We're going to be asked to identify the zeros of the function and the x-intercepts of the graph. Okay? So we've got 3 topics here. So standard form, zeros, and x-intercepts. So what do I mean standard form? What do I mean standard form? If our example is f of x equals x minus 2i times x plus 2i, okay, we're going to end up having to FOIL this one out, aren't we? Okay, the idea of standard form is well, if we just think quadratic, it's ax squared plus bx plus c, right? So in terms of higher powers, it's going just from highest power down to lowest power. So in this one, we are going to multiply out. So, you ready to FOIL with me? X times x is x squared. I'm doing this a long way, bear with me. X times 2i is 2ix is what I would say. And then negative 2i times x is minus 2ix. Negative 2i times positive 2i. What would your first answer be on that? Negative 2i times positive 2i. Negative 2 times positive 2. Negative 4, I times I squared. Right? Just doing the basic math here. Well, I say basic, but we're throwing in i's, so clean it up. Because we want standard form here. What do you notice when we clean that up?
2ix's cancel out.
Okay. 2ix minus 2ix is going to cancel out. I feel like I can use the tangerine here. It doesn't have to show up as well, right? To just cross something out. Are we okay with that? Can you handle that, Jacob? As long as I don't start writing a bunch in it. Okay. I don't even know what color I was on. I'm so not used to these colors. We have x squared. I don't want minus 4i squared. Standard form is not going to have any i's in it. What is minus 4i squared?
Positive 4.
Sound familiar? Because I squared is negative 1. And if I squared is negative 1, negative 4 times negative 1 is going to be positive 4. Okay, so that is what we call standard form. Okay, so we got our standard form there, yes? Next piece we're asked for is zeros. How do we find zeros? Nope, don't think that hard. She was talking about finding PRRs, but keep in mind, this was already in factored form, wasn't it?
Set each parenthesis equals 0.
Yeah, set each factor equal to 0, right? So in order to get zeros, we're going to set x minus 2i equals 0 and x plus 2i equals 0. And so when you solve those, we're going to come up with x equals positive 2i and x equals negative 2i. And what are those called? Those are my zeros. So zeros are what happen when you solve the equation. You're setting each factor equal to 0, right? You're solving that equation when you set equal to 0. What about x-intercepts? What x-intercepts do we have?
Is it the 2i and negative 2i?
Well, a lot of times our x-intercepts, I've taught over the years, right, that our x-intercepts are the same as our zeros. But in order for it to be an x-intercept of the graph, we need to be able to see it. Can I see an x-intercept of 2i? Can I see an x-intercept of negative 2i? And so your x-intercepts are your zeros, but it's your real zeros, your visible zeros. If you go back and graph the standard form, what do you notice about this graph? X squared plus 4. X squared plus 4. X squared is a parabola, and the plus 4 takes it up 4. Does this graph cross the x-axis? No. If you graph it on your calculator, to my knowledge, I don't know, maybe you guys might find stuff, but to my knowledge, you can't graph x minus 2i times x plus 2i.
No.
You would have to do the standard form. Okay? But when you graph that standard form, it's not going to touch the x-axis, right? So when we talk about x-intercepts, we're wanting the real zeros. So if there are real zeros, those would be x-intercepts. Since I only have imaginary zeros, then we're going to say there are no x-intercepts. And we're saying there's no x-intercepts because the zeros are imaginary. I did not leave myself enough room here. Sorry. Okay, questions on how that worked out? Okay, let's try B. Okay, f of x equals x minus 3 times x minus 3 times x minus square root of 2i times x plus square root of 2i. Note the comment here. It does mention, note that 3 has a multiplicity of 2. Okay, we'll talk about that here in a moment. Okay, how am I going to get standard form? Foil it. Can we do 2 and 2? Okay, and what's going to make life easier, folks? This square root of 2i, and it's kind of set up this way anyways, but the square root of 2i's, FOIL those together first before you mix in the x minus 3's. Okay, because multiplying the conjugates down here will make life a little bit better. So, what do we get when we FOIL x minus 3 times x minus 3? X squared minus 3x, and then another minus 3x, which is really going to be minus 6x, if you will. And then minus 3 times minus 3 is going to be plus 9. You guys, can you handle that first one? I was trying to go ahead and simplify it if you don't mind, so I guess holler at me if you don't like that. Okay, next two, as we FOIL these. I'm going to simplify them as I go too, if you'll let me. X times x is x squared. What do you notice that happens next since they're conjugates?
They cancel out.
My middle terms, my outsides and insides, my middle terms cancel out, right? Because we're going to have x times square root of 2i, and then x times negative square root of 2i. So you're going to have a positive square root of 2ix, and then a negative square root of 2ix. Do I have to write those down? No, you can, but you don't have to. I would go ahead and jump to the end. See how you feel about this one. What's negative square root of 2i times positive square root of 2i? Negative times a positive is a negative. Square root of 2 times square root of 2. What'd you say? Square root of 4, which turns out to be 2. What's I times I? I squared. What do you know about negative 2i squared? I squared is negative 1, so negative 1 times negative 2 really makes this positive 2. So you guys okay if I go ahead and just say that is x squared plus 2? Here's your side note information. Give it a little practice, and I feel like you guys will do that in your heads, but we're just getting into this, right? So I'm writing it out for you. Okay, what do I need to do next? We're multiplying again, right? We did the easy one, now we're multiplying again. I don't really have much of a preference, it's kind of up to you. What I'm probably going to do is take this x squared from the binomial, multiply it by the first 3, and then I'm going to take the 2 times from the binomial and multiply it by the first 3. Can we handle that? So if I multiply x squared by everything in the first one, x to the 4th minus 6x cubed plus 9x squared. Now multiplying everything in the trinomial by 2. So plus 2x squared minus 12x plus 18. And of course, as good mathematicians, we need to clean it up. I know there's x to the 4th. Do we only have the minus 6x cubed? Yes, we do. Minus 6x cubed plus 11x squared minus 12x plus 18. And what is this? That is standard form. Okay. After standard form, zeros. What do we have in the way of zeros? Or how are we finding zeros, I should say. Okay, we set each factor equal to 0, right? So if we set each factor equal to 0, I have x minus 3 equals 0, x minus 3 equals 0, x minus square root of 2i equals 0, x plus square root of 2i equals 0. Let's just say when I'm doing this in ink pen, I can squeeze this in a lot better than I can on the whiteboard here on the BenQ. What do we end up with here? We're going to have x equals what? 3. What else? Plus or minus square root of 2 times I. Can we write it like that? Yeah. Do I need to write 3 a second time? No. But realize this is an x to the 4th, isn't it? I should have 4 zeros. Why do I not have 4 zeros? Because that x minus 3 had a multiplicity of 2, and that accounts for 2 of them. Okay? So right there, those are your zeros. And finally, x-intercepts. What about your x-intercepts? 3? If we graph this standard form on the calculator, what should happen? This graph should cross the x-axis at 3, and then the other two are imaginary. So this time, we have a real x-intercept, and that is 3. So I'm going to say x equals 3, and again, that is my x-intercept. Okay, so if you graph, and that's, that's kind of a check, because you can get your zeros and your x-intercepts right, and you can mess up standard form, can't you? But that's kind of a check for yourself. If you put in that standard form and it's giving you the right 0 of 3, that should be reassuring that, hey, we're on the right track here, right? Okay. We're going to go ahead and look at the next one. I don't know that we'll get all the way through it. Let me rephrase that. We won't get all the way through it, but we'll start talking about it, okay? Example 2. Write a polynomial function of minimum degree. Notice they're not telling me what the degree is. In standard form, so specifically we want our final answer in standard form, with real coefficients whose zeros include -3, 4, and 2 minus I. Okay, so we're asked for standard form, whose zeros include those right there. Okay, here's my hint. F of x equals. Is that hinty enough for you? We've done this before.
3.
So a 0 of -3 is what as a factor? It is an x plus 3. Okay. A 0 of 4 is represented by the factor of x minus 4. A 0 of 2 minus I. Well, what do we always do? Officially, okay, what your brain may think is we just switch the sign. But what we're really always doing is we're really always doing x minus the 0. Because when you do x minus -3, guess what? That becomes plus 3. When you do x minus 4, that stays minus 4. So what we're going to say, and I'm going to write it the long way the first time, x minus the quantity, or the 0, of 2 minus I. Okay? Now, it just says minimum degree. So do we have the right number of zeros? We don't really know. But there's a catch. I need one more 0. I need one more 0, and this goes back up to the complex conjugate zeros theorem that's up above. I started because I said it would be important later on. What does the complex conjugate zeros theorem say? Given a function with real coefficients, if a plus bi is a 0, then so is its conjugate. Right here, we have 2 minus I. What is the conjugate of 2 minus I? 2 plus I. So guess what? That's part of the reason they only say minimum degree there. We're also going to have to put in here x minus the 0, 2 plus I. Okay. With that in mind, it would be way too easy if they'd let us leave it like this, wouldn't it? It specifically says to put it in standard form. And That's what we'll have to talk about tomorrow, is how to get it in standard form. Okay? There's going to be a little work. Okay? These problems in this lesson are doable, but they are tedious because they take a little work.